So next on the agenda, we have Anurag Bhatia with his presentation on distributed latency measurements. Anurag works at Global IP Backbone, Huracan Electric as network researcher. He is based out of India. He spends significant part of his time looking at the routing table, putting internal tooling to find routing anomalies. He has interest around peering, IXPs, IPv6, and DNS. Anurag, welcome, and the floor is yours.
Thank you, Elisa. Thanks a lot for the introduction, and I would like to express my thanks to the LACNIC team for accepting my talk, and also to my good friend Massimo for introducing me to this event. As Elisa introduced, I'm based out of India, so I'm sitting around 340 milliseconds away from you, not that far in the internet terms. And today I'll be presenting about distributed latency monitoring or measurement. Let me quickly start by sharing my screen. Elisa, can you please confirm if you can see my screen? Okay, great. So the idea for this presentation starts with looking for a smoke ping alternate. For those in the audience who may not know, smoke ping is an excellent tool for latency monitoring, and it's one of the tools which most of us have used as the starting option for doing latency monitoring. It has support for monitoring latency, packet loss based on ICMP. It supports a bunch of other protocols as well, HTTP, DNS resolution latency, and so on. Based on the various probes it comes with, and it has quick and easy config, and it has some basic alerting support that it can send an email. It can throw an error when it detects packet loss or high latency based on the threshold. Now, there are certain challenges with the smoke ping. Essentially, these challenges are more around the fact that it's hard to scale it up. So, if you are running different setup in terms of distributed setup, if you have say 10 POPs and with 10 different locations, and you have 10 different independent setups, it is hard to make them speak to each other, and ultimately you end up in getting a non-federated hard view. It's not possible to club graphs. Thus, as an example, if you are with 5 locations, 50 endpoints, you are going to potentially be looking at 250 plus graphs, which is quite a lot. You cannot really realistically expect operations team to be looking at large number of graphs on day-to-day basis to determine latency or packet loss issues. And lastly, it has limited alerting support. So while I said it has support for email, most of modern tools you would expect to have support for things like API calls, Slack, or various other push-based notifications on the chat tools. So I started looking for possible alternatives, and ultimately I want to monitor latency between different endpoints as part of my day-to-day job. Ultimately, you want to have various sources towards various destinations, kind of latency measurement, and an overall idea to aggregate that sort of view based on certain numbers. So maybe aggregate graphs based on the idea that all of them belong to same logical destination, logical city name, logical country name, any such grouping essentially. And it should be easier to monitor, besides latency, to monitor other things as well in the network, including monitoring servers or networking devices, application endpoints, and so on. This brings me to the idea of Prometheus. So I'm going to spend next few minutes on giving the idea about Prometheus before I jump back on the latency monitoring subject. So what is Prometheus? It's a tool which is essentially just a time series database. It allows you to store values in a time series database, and it makes them available over an HTTP endpoint. So that data can be queried over an HTTP endpoint by various tools. By default, it works on pull model, where Prometheus would pull metrics out from various endpoints, and these metrics can be just anything. This metric can be CPU utilization or memory, or as the case for this talk, latency as well. And by default, it speaks to agents over HTTP. And I use HTTP loosely here. You can make use of it over HTTP, where on the underlying part you have an encrypted tunnel running with some sort of encryption, or you could make use of it over HTTPS, any sort of encryption in place, essentially. And Prometheus can query these metrics from the endpoints at predefined regular intervals. Here's the basic design idea. Essentially, in the center, you have Prometheus storing these metrics. It can make use of these pull metrics from various set of exporters. Different exporters add different features, essentially. So you have different exporters, say, for monitoring compute or monitoring containers or monitoring SNMP interfaces or monitoring latency. And it has support for alert manager for pushing alerts, and of course the great Grafana, the great open source tool for graphing the values which are collected by the time series database here. So concept which if you have not used Prometheus before, you need to take away is that everything here is metrics. Whatever you are storing, it can be interpreted, it can be graphed in any way it's needed. And because it's all stored in a time series database, one can make use of averaging as well. So in day-to-day world, you may want to have absolute live non-average view for certain links, but at the same time, you may want to have average view for certain other links. So if I'm measuring my latency to say somewhere like Panama City with 340 milliseconds, I may be averaging it out with based on 5 minutes or 10 minutes average, or I may be averaging or may be graphing the actual view while having an average before alerts are sent out. One can add various labels. So whatever metrics you're storing, it can have any labels. As an example, you can have something like destination country, Hong Kong, destination type cloud, if you want to monitor certain cloud players in Hong Kong, just as an example. And it supports for alerting based on the alert manager on the predefined rules, which can be based on a specific lookup or a group of lookups and so on. So it's quite flexible that way. So here's an example of metrics. I'm essentially pulling out metrics from one of the exporters on this server, which is just giving me these values. So you have a key and a value and certain labels attached to it. So let me jump next onto the specific exporter which I'm covering in this talk. So. Besides various exporters, one of the popular exporter in Prometheus is black box exporter, which can be used for the latency monitoring. What is it? Essentially, it's an open source probing endpoint. It can be installed. It's a simple Go based tool. So and also it also comes as a container. So one can deploy it as a container or a simple Go package on any sort of hardware. It can go on a server, or it can go on even on a device like Raspberry Pi or any low end compute device. It supports monitoring of HTTP, HTTPS, DNS, TCP, ICMP, and gRPC. Essentially, when you are monitoring, say, an ICMP endpoint, it will monitor the ICMP latency. If you are monitoring, say, an HTTP endpoint, it would monitor a bunch of things like how long it took on the DNS resolution for that endpoint, how long it took to connect, and so on. And because it's written in Go, it's a single binary. It can be easily downloaded and executed. No, not really any major dependencies as such. Here's an example of probing one of the servers running it. So normally you would not do this sort of probing when you're running it live, but this is just to have just for understanding. I'm essentially probing it to an endpoint. So this endpoint is running on my server on a VPN endpoint, and I'm saying this should use module ICMP4 for ICMP version 4, and target essentially here is for HE.net, and we get the values out. So you can focus on the values here, somewhere in middle. It is giving resolution latency. It is giving the RTT, the latency, which is 0.260. And because this is in seconds, you are looking at around 260 millisecond of latency here, which sounds reasonable, by the way. And the setup latency and so on. So these in this setup, I'm just probing it manually. In case of Prometheus, you would expect it to be probing it on its own. Here's another example. I'm just probing for SANOG, which is the South Asian NOG, SANOG.org domain, and instead of ICMP, I'm looking for HTTP latency. So again, you see more detailed output here. So we are essentially getting probe HTTP duration, and the values here are for connect, processing, resolve, and TLS, and all these values are essentially in seconds. I think the server is probably somewhere in Singapore, and I'm probing here on one of my servers in Ashburn. Here's a simple configuration example in Prometheus where you essentially put it in Prometheus and then Prometheus does this probing for you. And this can be quite different for individual endpoints. You can say I want to measure some endpoints every 1 minute, or certain endpoints only once in few minutes, once in half an hour, or whatever. So here's a case of single monitoring. I'm just monitoring the latency to the ISP's WAN IP at my home, and I'm adding certain labels like destination, which is public, name, just a logical name, because at times you might be monitoring things which do not have DNS name, and the region India. Now, based on these labels, I can extract this data out in Grafana or any other similar tool. On the right side, again, similar config, but just that we have multiple targets all attached with the same set of label. So I've used DNS in this case. Is just bunch of Indian speed test servers, Ookla speed test servers, for monitoring latency against those, and all of them are being attached with this label public and label India. So the label is not that important here, what I'm using, but it's just to categorize in whatever way fits your specific use case. Here's an example of Prometheus query. So I'm querying in this case for the probe ICMP duration second. So I'm saying, show me the ICMP latency, and the region is Hong Kong. So it is showing me all the things in the database for the region Hong Kong, and you see various set of latencies. It is including the resolve, RTT, setup, latency for each endpoint I have. And it is also coming from different jobs. So because we are querying database without specifying the job name, it is showing me the latency from all the probes I'm using. And this specific test setup has 6 different servers around the world for measuring latency. So it is showing me latency from all those 6 different set of servers, geographically diversified towards Hong Kong endpoints, which is here in this case is hknog.net and hkpn.net, one of the ISPs there, with the values on the right. Now, you would not use Prometheus for Prometheus web interface for this sort of monitoring. This is good for troubleshooting, but in majority of cases you would do it with Grafana, which I cover in next few slides. But just for the sake of understanding, here's the database and here's the view of the database. One more query example. In this case, I'm just turning a little more specific. So I'm saying, besides region Hong Kong, show me just the round trip latency. I don't want the other latency. And instead of showing it for all, just show me for HKNOG, which is the Hong Kong NOG. Just show me for HongKongNOG.net. So you see from my 6 different servers, the latency in seconds. And because while this is in seconds, one can easily do something like star 1000, and you would see now latency in milliseconds. So it's quite flexible that way for the measurement. Going further, here's an example of Prometheus essentially querying for something like the same query, but graphing it out. So Prometheus web interface has inbuilt graphs. This is showing us graph for exact same query which I did earlier. Again, these graphs are mostly for quick troubleshooting. You typically not use these as full-fledged graphs. Most of people would have something like Grafana set up for fixed permanent graphs as such. Now, whatever can be queried here can be plotted, because all this is going in a time series database, whether it's CPU metrics or latency metrics or packet loss metrics, all of that can be plotted. So here's an example of plotting the same over, or in case of Grafana, and in the bottom you can find out the job. So I'm just giving the exact same query just for a different endpoint as I did before, except that I'm adding the averaging over time here as a function. And in the end, I'm also adding one line saying, don't show me values with 0, because essentially, if you don't put that, you will see suddenly graph going to 0, and which would give you absolute meaningless thing. It is showing that latency during an outage, latency reduced to 0 milliseconds, which makes no sense. So you would typically exclude values with 0 if an endpoint is somehow going down. So you see this latency, and you see spike at this point of time within the Grafana interface. Now this can be placed where it can be kept permanently based on certain logical mapping. Here's one more example case. So this time again, averaging over time, and this time averaging for 5 minutes for this specific graphs, and you see latency jumps happening between this endpoint. Both of these endpoints, by the way, are within India, and I see jumps during one of the issues time, and it's actually fun to watch this sort of problems. Now, the powerful part with Grafana and Prometheus comes is with the grouping factor. So here's another query, and this time I'm not putting the raw query. So in case of Grafana, you can put the raw code, or you can just go in the builder mode and just do the click and select kind of interface. So I've selected the job from one of my servers in Mumbai. The phase is entity, and instead of phase is RTT, sorry, and the region in this case is Europe. So I'm not saying any specific endpoint in Europe, but I'm saying all the things with Europe as the endpoints. And you see various graphs of servers in various Hetzner, Contabo, a couple of endpoints on Dutch Telecom, Backblaze, and so on. Just some of the public endpoints as a demo. And you see latency. And the Grafana interface allows you to select by. So while this is slide, so it won't work. But if this is a Grafana interface, I could have clicked in there, clicked on one of the values there. It will only show me that specific graph. So you can operationally view large number of graphs while focusing on one single graph if you need to. So something like this, if latency is increasing, I could just select this one and watch out for that. A more complicated one. Here's an example for latency towards various anycast prefixes of root DNS from one of the ISPs at home. So I maintain multiple ISPs at home, and there is a black box exporter running behind each of them as a container with a policy-based routing. So this is showing me latency towards each of the root DNS servers over time. I think this is for 30 days, 30 days worth of data. So it's kind of fun to watch and figure out when suddenly you see changes in latency happening. I'll proceed after the Grafana graphs here. So whatever can be queried here can be used to give alerts, and this is quite powerful mechanism. So here's some of the sample configs for generating alerts in Alert Manager. It's a separate tool which runs in the same ecosystem, which connects to Prometheus instance, and essentially I'm saying, give me an alert if hk.not latency goes above 120 milliseconds, and it is 120 milliseconds for more than 5 minutes. So in this case, the expression is exactly same as I showed you earlier, just that in the end I have greater than 0.12, essentially saying, show me the data whenever it's more than 0.12 seconds or 120 milliseconds, and just adding a bunch of labels to it as you see fit, just as a demo. Or here's another example, which is saying, show alert if latency from, say, Germany goes above 300 milliseconds. So same set of values as you saw in the previous slide, just that saying greater than 0.3, which is 300 milliseconds for over 5 minutes. Operationally, you may want to run this sort of alert only for your own destinations or for the really critical ones, and usually with a higher averaging. If you run it with too low averages, even a single spike in latency would send you too many alerts. So you may want to do certain averaging or certain for values here, so that you don't get overloaded with alerts. Here's an example of how you receive an alert. This is a case with alert on email, but it supports various push mechanisms. So you can do it over various chat-based applications which exist these days with push notification. Now, one of the advantage of this ecosystem is that it supports scaling up, so it can really scale up well. By default, Prometheus runs as a single instance, but if you have a massive requirement with lots and lots of locations, lots of endpoints, you can in theory run a different Prometheus instance at different location and have a federated view. It also supports, there are various other open source packages and tools like Thanos or Cortex or Victoria Metrics, which allows you to store these long-term data on a S3 endpoint. So I personally use Thanos in my setup, and I store all these metrics on a S3 endpoint, which gives me a pretty high scalability. You can run your own S3 endpoint on your own large storage servers, or you could go with whatever cloud player of your choice. How this all fits in, here's an example of some of the earlier latency charts from SmokePing for, say, some of the networks in Thailand. And here's what you see in in Grafana. Essentially, two set of graphs, all with aggregated values. with certain numbers, and one from Nuremberg, Germany towards German endpoints, one from Mumbai, Germany towards endpoint. I could even aggregate this further in a single graph if there's a fit in there. I'll quickly proceed. I think I don't have much time left, so I'll probably rush through the remaining slides. What about the part distributed here? Well, this is where the power of RIPE-ATLAS comes in. I hope you're familiar with RIPE-ATLAS. If you are not, I think our good friend Michela Galante from RIPE NCC is there present locally. Please do speak to her if you have questions about RIPE-ATLAS. But it's essentially a large-scale distributed monitoring project. So if you have used RIPE-ATLAS, you might have seen a problem where you can trigger ad hoc measurements, but how do you fit it in your system? So here's a case. You can run a RIPE-ATLAS exporter and look for specific measurement. In this case, I'm saying the measurement ID, and you get these values within the instance. So this is again a sample configuration where I am sending packets from various Starlink probes just for fun to a bunch of my locations, and here's how the graphs look like. So all this data is coming from RIPE-ATLAS in the same Grafana instance. So the same set of charts which are showing from my network are also showing it from the RIPE-ATLAS probes, which makes it really powerful. Another case for distributed latency monitoring, you can make use of things like Google as well. So I do that quite a bit with my good friends from India, where they are very much interested in monitoring the latency from Google. One can make use of it by running stateless containers on Google Cloud Run as a black box exporter, and you get same set of charts. But that's broadly the idea. So summary in the end, Metrics Word is becoming really standard for tooling. If you have not used it so far, please do explore it. It's really good and develop tooling. And there are many components
Anurag,
which you may or may not need.
Anurag, we're out of time. If you can begin to close the presentation. Thank you.
Okay, sure. If you have any questions, feel free to write me. Email is there. Thank you. Thank you, Elisa.
Thank you, Anurag. Sorry that we were already a bit